Okay, let's see the solution of test number 16. The question is, two metal plates are connected with two coil springs. A DC voltage source with delta V equal to 100 volt and switch S as shown in the figure. Initially, there is no charge on the metal plate. The distance between plates is D equal to 8 mm and the capacitance of the plate is C equal to 2 microfarad. After S is closed, the distance between plates is reduced to D over 2. What is the value of spring constant K? Okay. How can we analyze this problem? Okay. Here we can see that when we put the charge on the capacitor here, the spring, the distance between the plate reduced to D over 2. It means that the spring is stretched. Okay, from the equilibrium position. Okay, initially there is no charge on the plate, and the spring is in the equilibrium position, and then it stretched with the distance of half of the D over 2, right? Because we know that the gap between the plate reduced to D over 2. It means that from symmetry, we know that each spring stretched with the same distance. So it is a half of the D over 2, which means the D over 4. And when we stretch the spring, it means that there is a force act on the spring. The question is, where is this force come from? Okay. We can describe this quite easily. When we have parallel plate capacitor, okay, with the positive charge on one side and negative charge on the other side, we know that in between we have the electric field that comes from the positive charge and the electric field that comes from the negative charge. And we have the charge on each plate. We have the positive Q on this plate and negative Q on this plate. It means that this electric field will exert a force on the charge. Okay, but the point is that the force that exerts on the charge, the positive Q, comes from the electric field from the negative charge, or it is a E minus, and the force on the negative charge minus Q comes from the electric field from the positive charge. Which means that the electric field from the positive charge will not interact with itself. We cannot have the self interaction between the electric field and the charge. It means that if a charge produces an electric field, that field will not interact with itself. Okay, so we know that. So it means that this electric field E minus will exert force on the positive Q, and E plus will exert the force on the negative Q. And we can see that the electric force on the positive plate will point in this direction, and the electric force on the negative plate will point in this direction, because the force on the negative charge will point in the opposite direction of the electric field, right? And if we connect this with a spring, okay, you can see that this electric force will stretch the spring, and from symmetry we know that the distance that the spring stretched from its equilibrium position is equal to D over 4, right? It is because the plate come closer, and the gap between the plate become d over 2. Okay, the half of d over 2 is d over 4. Okay, so when the situation here is that it is an equilibrium configuration, it means that the force, the electric force balance with the restoring force from the spring. So when we equate that force, we will be able to calculate the spring constant. Okay, now let's go to the detail. To calculate the force, we must first know the electric field, and we have discussed this before, that the electric field between the capacitor from the positive charge and from the negative charge will have the same magnitude, and the same direction. So we must have E plus equal to E minus, which is equal to the sigma over 2E. Okay, if you remember, we know that the total electric field between the parallel plate capacitor is sigma over epsilon. So the electric field from positive and negative charge, the magnitude is half of this total electric field. So we have that E plus and E minus equal to sigma over 2 epsilon naught. Okay, and this sigma is a charge density per area. So this sigma is Q over A, where Q is a charge on the plate and A is the area of the plate, right? And we can find Q from the definition of the capacitor. That is, we know that Q is equal to C delta V, right? But this C must be the capacitor at equilibrium, right? Must be the capacitor at equilibrium. So if we assume that at equilibrium the capacitor is C prime, okay, so we have Q is equal to C prime. Now we don't know the value of C prime, but we can calculate it from the initial capacitor C, because we know that at the initial configuration the capacity of these two plates is 2 microfarad. And after we put the charge on this plate, the gap reduced to d over 2. We know that for the parallel plate capacitor, we have that C is equal to epsilon naught A over D. Okay. The capacitance is inversely proportional to the gap between the plate. So it means that if the gap reduced to the half of the initial value, the capacitor will increase 2 times to the initial value. So we can find that C prime, which is the capacitor when our system is in equilibrium, must equal to the 2 times C, where the C is the initial capacitor, which we know the value, which is 2 microfarad. Okay, so we put this C prime to here. This C prime is equal to 2C. We put C prime, Q equal to C prime delta V, and C prime is equal to 2C. So we have Q is equal to 2C delta V, and this is the expression for the electric field. Now, the force, for example, if we look at the force on the positive plate, it must be equal to the charge times the field. But as we discussed, this is the field from the negative plate. Okay, and we know the field from the negative plate. We know the Q is equal to C prime delta V or 2C delta V, and we substitute this, and we get this F plus is equal to this. And we know from symmetry that the F minus, the magnitude of the F minus will equal to the magnitude of F plus, but point in the opposite direction. Okay, and the force, the restoring force on these two springs are equal also. And since the force, the spring stretch by the distance dE over 4, so the magnitude of the restoring force must be K times D over 4, which is equal to the magnitude of the electric field. Okay, but the direction of the restoring force and the electric force are opposite, right? Okay. Here we are interested only on the magnitude, so we have this relation. Okay. Now, we need some trick from the relation, from the expression of the capacitor. Okay. We know that C is equal to epsilon naught A over D. This is the initial capacitance, and this is the formula for the capacitance of a parallel plate capacitor. Okay. And from this expression, this term, if we rearrange a little bit by write this term epsilon naught A to be epsilon naught A over D times D like this, and then we can substitute this epsilon naught A over D equal to C, so we have this C here. Now this 2C can cancel this 2C squared to get this 2C. Okay, so we have that this term become 2C times delta V squared over D, which equal to K times D over 4, and then rearrange this to get that K is equal to 8C times delta V squared over D squared. Okay, and we know the numerical value of C, delta V, and D, right? C is 2 microfarad. But when we use this to calculate, in our calculation, we have to change it to the base unit, which is the 2 times 10 to the minus 6 farad. That is for the microfarad. 10 to the minus 6 farad. Okay, delta V is 100 volt, it's okay, the unit is okay, and D is 8 millimeter. 8 millimeter have to convert to the base unit as the 8 times 10 to the minus 3 meter. Before substitute into this expression, and when you do the numerical calculation, you will get that K is equal to 2.5 times 10 cube Newton per meter, or 2.5 kilonewton per meter. So the answer is K is equal to 2.5 times 10 cube Newton per meter, or 2.5 kilonewton per meter.